Synapse Global Institute. My name is Elizabeth, your lecturer for Quantitative Technique 1, and it is a pleasure to begin this journey with you as CPA students. As we move through today's session, please feel free to use the chat section at any point to ask questions or request clarification, because understanding the foundations thoroughly is essential for success in quantitative analysis. We begin by focusing on functions. By the end of this section, you should be able to understand the definition and basic properties of functions, identify different types of functions together with their graphical representations, apply functions to solve business-related problems, and interpret real-world applications of functions in business contexts. A function is a mathematical relationship between two sets, known as the domain, which is the input set, and the codomain, which is the output set. A function assigns each element of the domain to exactly one element of the codomain. In simple terms, for every input, there is one and only one corresponding output. This idea of one clear output for each input is what distinguishes a function from other types of relationships. A function can be written in general form as f mapping x to y. Here, f is the function name, x represents the domain or the set of all possible inputs, and y represents the codomain or the set of all possible outputs. Mathematically, a function maps an element x from the domain x to an element f multiplied by x in the codomain y, and this relationship is expressed as f multiplied by x equals y. In this expression, x is the input or independent variable, while y, which is equal to f multiplied by x, is the output or dependent variable. Functions are widely used in business to model relationships between variables. For example, a company may use a function to model its revenue, denoted by R, based on the number of units sold, denoted by Q. If at any point this notation feels abstract, do pause me through the chat, and we will unpack it carefully. Functions can take several forms, and there are a number of common types that you will encounter frequently in business analysis. A linear function is one where the relationship between the input x and the output y forms a straight line. Its general form is y equals mx plus b. In this sentence, m represents the slope, which is the rate of change, and b represents the y-intercept, which is the value of y when x equals 0. In business applications, linear functions are often used to model relationships such as cost C and output Q, where cost increases in a constant, predictable way as production increases. Another important type is the quadratic function. A quadratic function is a polynomial function of degree 2, and its graph is a parabola. The general form is y equals ax squared plus bx plus c. Here a, b, and c are constants. In business, quadratic functions are especially useful for modeling profit maximization, where profit may increase as sales increase up to a certain point and then begin to decrease due to factors such as rising costs or diminishing returns. We also have cubic functions, which are polynomial functions of degree 3. The general form is y equals ax cubed plus bx squared plus cx plus d, where a, b, c, and d are constants. These functions can model more complex business situations, particularly where relationships are nonlinear, such as certain supply and demand patterns that do not follow simple straight lines or parabolic shapes. Exponential functions are used to model growth or decay at a constant percentage rate. An exponential function is given by y equals a multiplied by b raised to the power of x. In this expression, R is the initial value when x equals 0, and b is the growth rate, with b being greater than 0. In business contexts, exponential functions are commonly used for compound interest calculations, population growth analysis, and modeling the growth of investments over time. If you are familiar with interest accumulating faster as time goes on, that accelerating behavior is exactly what exponential functions capture. Closely related to exponential functions are logarithmic functions, which are their inverse. A logarithmic function has the form y equals a multiplied by log base b of x. In this case, a is a constant, b is the base of the logarithm, which is usually e or 10, and x is the independent variable. Logarithmic functions are useful in business for modeling diminishing returns, where growth happens rapidly at first, but then slows down over time. Graphs of functions play a critical role in helping us visually interpret relationships between inputs and outputs. A linear function produces a straight line graph, a quadratic function produces a parabolic curve, an exponential function produces a J-shaped curve, and a logarithmic function produces a curve that flattens out as the input increases. Understanding these graphs allows you to predict how one variable will behave when another variable changes, which is a vital skill in business decision-making. If you are unsure about how any of these graphs look or behave, please ask in the chat, and we will explore them together. Functions are widely applied in business to model real-world situations. Linear functions are commonly used in cost and revenue modeling, showing how total cost or total revenue changes with the number of units produced or sold, often increasing by a fixed amount for each additional unit. Quadratic functions are frequently used in profit modeling, where profit rises with increased sales up to an optimal point and then falls beyond that point. Exponential functions are used to model investment growth over time, when returns are reinvested and grow at a constant rate. Logarithmic functions can be used to model depreciation of assets, where the value of an asset falls rapidly at first and then more slowly as time goes on. Let us now work through the practice questions, and I encourage you to actively follow each step and use the chat if any calculation is unclear. In the first question, a company's revenue function is given by R multiplied by x equals 20x plus 500, where x is the number of units sold. In part A, we are asked to calculate the revenue when 40 units are sold. For x equals 40, R multiplied by 40 equals 20 multiplied by 40 plus 500, which equals 800 plus 500, giving 1300. Therefore, the revenue when 40 units are sold is $1,300. In part B, if the company sells 100 units, R multiplied by 100 equals 20 multiplied by 100 plus 500, which equals 2,000 plus 500, giving 2,500. The revenue when 100 units are sold is $2,500. In part C, the constant 500 represents the fixed revenue, meaning the revenue the company receives even if no units are sold, that is, when x equals 0. In the second question, a firm's profit function is given by P multiplied by x equals negative 3x squared plus 150x minus 500, where x is the number of units sold. In part A, to calculate the profit when 10 units are sold, we substitute x equals 10 into the function. P multiplied by 10 equals negative 3 multiplied by 10 squared plus 150 multiplied by 10 minus 500. This equals negative 300 plus 1500 minus 500, which gives 700. Therefore, the profit when 10 units are sold is $700. In part B, we are asked how many units must be sold to achieve maximum profit. The maximum profit occurs at the vertex of the parabola, which is given by x equals minus b divided by 2a. For this function, a equals negative 3 and b equals 150. Substituting these values, x equals minus 150 divided by 2 multiplied by negative 3, which simplifies to 150 divided by 6, giving 25. Thus, the company must sell 25 units to achieve maximum profit. To find the maximum profit itself, we substitute x equals 25 back into the profit function. p multiplied by 25 equals negative 3 multiplied by 25 squared plus 150 multiplied by 25 minus 500, which equals negative 1875 plus 3750 minus 500, giving 1375. Therefore, the maximum profit is $1,375, achieved when 25 units are sold. As we pause here, please remember that questions are a vital part of learning, so do not hesitate to use the chat to ask for clarification on any concept, calculation, or interpretation we have covered. At this point, I encourage you to pause, take a 5-minute break, refresh your mind, and then return ready to continue, in line with the flexible Synapse learning model. We now continue with the next part of our discussion, building directly on what we have already covered. Please remember to make active use of the chat section if anything needs clarification, because these ideas form a critical foundation for later topics in quantitative analysis. In this section, our focus is on functions, equations, inequalities, and graphs, specifically linear, quadratic, cubic, exponential, and logarithmic functions. By the end of this section, you should be able to understand the concepts of functions, equations, and inequalities, identify and graph these different types of functions, apply them to solve business-related problems, solve equations and inequalities associated with them, and interpret their graphical representations in business contexts. A function relates an input, which is the independent variable, to an output, which is the dependent variable, through a well-defined rule or relationship. This relationship can be expressed as f multiplied by x equals y, where x represents the input and y represents the output. An equation is a mathematical statement that asserts the equality of two expressions, and solving an equation involves finding the values of the variables that make this equality true. An inequality, on the other hand, compares two expressions and shows that one is greater than or less than the other. Inequalities are particularly important in business because they are used to model constraints, such as budget limits or production capacities. For example, the equation 3x plus 2 equals 14 can be solved to find the exact value of x, while the inequality 3x plus 2 is less than or equal to 14 expresses a restriction where x cannot exceed a certain value. If the distinction between equations and inequalities is not fully clear, please raise it in the chat so we can discuss it further. We now consider the main types of functions in turn, starting with linear functions. A linear function is one in which the relationship between the independent variable x and the dependent variable y is constant, and its graph is a straight line. The general form of a linear function is y equals mx plus b. In this expression, m represents the slope, meaning the rate of change of y with respect to x, and b represents the y-intercept, which is the value of y when x equals 0. When we look at the graph of a linear function, as illustrated in the diagram provided, the straight line clearly shows this constant rate of change. If m is positive, the line rises from left to right, and if m is negative, the line falls from left to right. This visual behavior is essential for interpreting trends in business data. In business applications, linear functions are commonly used to model cost and revenue. For example, if a company sells a product for £10 per unit, the revenue from selling X units can be modeled as R multiplied by X equals 10X. This tells us that revenue increases by £10 for every additional unit sold, a simple but powerful representation of a business relationship. We then move to quadratic functions. A quadratic function is a polynomial function of degree 2, and its graph is a parabola. Its general form is y equals ax squared plus bx plus c, where a, b, and c are constants. The value of a determines the direction in which the parabola opens. If a is positive, the parabola opens upwards, and if a is negative, the parabola opens downwards. The graph shown in the material demonstrates this parabolic shape clearly, and it also highlights the vertex, which represents either the maximum or minimum value of the function, depending on the sign of A. In business, quadratic functions are particularly useful for modeling profit maximization. For example, a profit function, such as p multiplied by x equals negative 2x squared plus 40x minus 200 can be used to show how profit changes as the number of units sold increases, with the maximum profit occurring at the vertex of the parabola. Next, we consider cubic functions. A cubic function is a polynomial function of degree 3, and its general form is y equals ax cubed plus bx squared plus cx plus d, where a, b, c, and d are constants. The graph of a cubic function, as shown in the diagram, can have one or two turning points and may increase and decrease over different parts of its domain, often forming an S-shaped curve. In business contexts, cubic functions are useful for modeling more complex situations, such as nonlinear supply and demand relationships, or cases where price elasticity changes at different levels of output. We then turn to exponential functions. An exponential function models growth or decay where the rate of change is proportional to the current value. It is given by y equals a multiplied by b raised to the power of x. In this expression, a is the initial value when x equals 0, and b is the growth rate, with b being greater than 0. The graph of an exponential function shows rapid growth if b is greater than 1, or rapid decay if b lies between 0 and 1. The curve increases or decreases at an accelerating rate, as clearly illustrated in the provided graph. In business, exponential functions are widely used in compound interest calculations, population growth analysis, and investment growth. For example, the value of an investment growing at a constant interest rate, R over time t, can be expressed as v multiplied by t equals p multiplied by 1 plus r raised to the power of t. Logarithmic functions are the inverse of exponential functions. A logarithmic function has the form y equals a multiplied by log base b of x, where r is a constant, b is the base of the logarithm, usually e or 10, and x is the independent variable. The graph of a logarithmic function, as shown in the material, starts at negative infinity and increases slowly as x increases. The curve approaches but never reaches the vertical axis, which acts as an asymptote. In business applications, logarithmic functions are useful for modeling diminishing returns, where profit or output increases rapidly at first, but then grows more slowly as production expands further. When we compare the graphical representations of these functions, several key patterns emerge. A linear function appears as a straight line with a constant rate of change. A quadratic function appears as a parabola that is symmetric about its vertex. A cubic function appears as an S-shaped curve with up to 2 turning points. An exponential function appears as a rapidly increasing or decreasing curve representing growth or decay. A logarithmic function appears as a curve that increases slowly, representing diminishing returns. Being able to recognize these shapes quickly is an important analytical skill in business decision-making. Let us now work carefully through the practice questions, and again I encourage you to use the chat if any step is unclear. In the first question, the demand function for a product is given as d multiplied by x equals 5x plus 50, where x is the number of units sold. In part A, when x equals 20, d multiplied by 20 equals 5 multiplied by 20 plus 50, which equals 100 plus 50, giving 150. Therefore, the demand when 20 units are sold is 150 units. In part B, if the price per unit is £20, total revenue is calculated as price per unit multiplied by demand. This gives revenue equals 20 multiplied by 150, which equals 3,000. Thus, the total revenue is £3,000. In the second question, a company's profit is given by the quadratic function p multiplied by x equals negative 4x squared plus 60x minus 200, where x is the number of units sold. In part A, for x equals 10, p multiplied by 10 equals negative 4 multiplied by 10 squared plus 60 multiplied by 10 minus 200, which equals negative 400 plus 600 minus 200, giving 0. Therefore, the profit when 10 units are sold is £0. In part B, the maximum profit occurs at the vertex of the parabola, which is given by x equals minus b divided by 2a. Here, a equals negative 4 and b equals 60, so x equals minus 60 divided by 2 multiplied by negative 4, which simplifies to 60 divided by 8, giving 7.5. Since the number of units must be an integer, the company must sell approximately 8 units to achieve maximum profit. Substituting x equals 7.5 back into the profit function gives p multiplied by 7.5 equals negative 4 multiplied by 7.5 squared plus 60 multiplied by 7.5 minus 200, which evaluates to 25. Thus, the maximum profit is £25. We then consider a further example where the profit function, measured in thousands of shillings, is given as p multiplied by x equals negative 2x cubed plus 9x squared plus 12x minus 5, where x represents the number of units sold in hundreds. To find the number of units that maximizes profit, we first differentiate p multiplied by x with respect to x, giving p dash multiplied by x equals negative 6x squared plus 18x plus 12. Setting this equal to 0 gives negative 6x squared plus 18x plus 12 equals 0, which simplifies to x squared minus 3x minus 2 equals 0. Solving this quadratic gives x equals 3 plus or minus the square root of 17 divided by 2, producing approximate values of 3.56 and negative 0.56. Using the second derivative test, we find that the maximum profit occurs at x approximately equal to 3.56, meaning about 356 units. Substituting x equals 3.56 into the original profit function gives a maximum profit of approximately 61.59 thousand shillings, which is about 61,590 shillings. The accompanying graph of the profit function visually confirms this result by showing the peak at around this level of output. As we conclude this part of the lecture, please take a moment to reflect on how equations, inequalities, and different types of functions work together to model real business situations. Do use the chat to raise any questions now or later, as clarity at this stage is crucial. I now encourage you to pause, take a 5-minute break, and then return refreshed and ready to continue, in line with the flexible Synapse learning model. We now continue seamlessly with the application of mathematical functions in solving business problems. As always, please use the chat section freely if any step, interpretation, or calculation needs clarification, because applying these ideas correctly is central to sound business decision-making. By the end of this section, you should be able to understand how different types of mathematical functions are used to solve real-world business problems, apply linear, quadratic, cubic, exponential, and logarithmic functions to model and solve business situations, interpret the results of mathematical models in business contexts, and use these models to make informed decisions such as maximizing profit, minimizing cost, and forecasting future trends. Mathematical functions are powerful tools in business because they allow us to model relationships between variables in a structured and logical way, helping managers and analysts move from raw data to informed conclusions. We begin with revenue and cost analysis using linear functions. A linear function can be used to model the relationship between the number of units sold and the revenue or cost of a business. The total revenue generated from selling X units of a product can be expressed as R multiplied by X equals P multiplied by X. In this expression, R multiplied by X represents revenue, P represents the price per unit, and X represents the number of units sold. Similarly, a cost function can be written as C multiplied by X equals F plus V multiplied by X, where C multiplied by X is the total cost, F is the fixed cost that does not depend on the number of units sold, V is the variable cost per unit, and X is the number of units produced or sold. To see how this works in practice, consider a company that sells a product for £50 per unit, has a fixed cost of £2,000, and a variable cost of £30 per unit. The revenue function is R multiplied by X equals 50X, and the cost function is C multiplied by X equals 2000 plus 30X. If the company sells 100 units, revenue is R multiplied by 100 equals 50 multiplied by 100, which gives 5,000, and cost is C multiplied by 100 equals 2000 plus 30 multiplied by 100, which also gives 5,000. In this situation, the company breaks even at 100 units sold because revenue equals cost. We now turn to profit maximization using quadratic functions. A quadratic function is frequently used to model profit, because profit often increases as sales increase, reaches a maximum point, and then begins to decrease due to diminishing returns. A quadratic profit function can be written as P multiplied by X equals AX squared plus BX plus C, where P multiplied by X is profit, X is the number of units sold, and A, B, and C are constants. The vertex of the parabola represented by this function gives the maximum profit when R is negative, or the minimum profit when R is positive. For example, consider the profit function P multiplied by X equals negative 2X squared plus 40X minus 200. To find the number of units that yield the maximum profit, we use the vertex formula, which states that X equals minus B divided by 2A. In this case, R is negative 2 and B is 40, so X equals minus 40 divided by 2 multiplied by negative 2, which simplifies to 40 divided by 4, giving 10. This means the maximum profit is achieved when 10 units are sold. Substituting X equals 10 back into the profit function gives P multiplied by 10 equals negative 2 multiplied by 10 squared plus 40 multiplied by 10 minus 200, which equals negative 200 plus 400 minus 200, giving 0. This tells us that the maximum profit is £0, indicating a break-even point. Next, we examine forecasting growth using exponential functions. Exponential functions are particularly useful when growth or decay occurs at a constant percentage rate over time. The general form of an exponential growth function is y equals a multiplied by b raised to the power of x, where y is the quantity after x periods of growth, r is the initial value, b is the growth rate, and x represents time. When b is greater than 1, the function models growth, and when b lies between 0 and 1, it models decay. As an illustration, suppose a company's sales grow by 5% per year, and initial sales are £100,000. The sales after t years can be modeled as S multiplied by t equals 100,000 multiplied by 1.05 raised to the power of t. After 3 years, S multiplied by 3 equals 100,000 multiplied by 1.05 raised to the power of 3, which is approximately 115,762.5. This shows that sales after 3 years are approximately £115,762.50. We now consider depreciation of assets using logarithmic functions. Logarithmic functions are useful when change happens rapidly at first and then slows over time, which is common in asset depreciation. The general form of a logarithmic depreciation function is v multiplied by t equals a multiplied by log base b of t, where v multiplied by t is the value of the asset at time t, a is the initial value, b is the base of the logarithm, and t represents time. For example, if a machine has an initial value of £10,000 and depreciates according to the function v multiplied by t equals 10,000 multiplied by log base 10 of t, then after 5 years the value is v multiplied by 5 equals 10,000 multiplied by log base 10 of 5, which is approximately 10,000 multiplied by 2.32, giving 23,200. This numerical result follows directly from the mathematical model provided. Beyond these examples, mathematical functions have several additional business applications. Demand and supply functions are often linear and show how price and quantity are related. Market equilibrium can be found by setting demand equal to supply and solving for the price or quantity. Break-even analysis commonly uses linear or quadratic functions and occurs when total revenue equals total cost. We now work carefully through the practice questions. In the first question, a company's cost function is C multiplied by X equals 500 plus 20X, and the revenue function is R multiplied by X equals 50X, where X is the number of units produced and sold. To find the break-even point, we set revenue equal to cost. This gives 50X equals 500 plus 20X. Subtracting 20x from both sides gives 30x equals 500, so x equals 500 divided by 30, which is approximately 16.67. This means the company needs to sell approximately 17 units to break even. The break-even revenue is found by substituting x equals 17 into the revenue function, giving R multiplied by 17 equals 50 multiplied by 17, which equals £850. In the second question, a company's profit function is P multiplied by X equals negative 5X squared plus 40X minus 100. The maximum profit occurs at the vertex of the parabola. Using the vertex formula, X equals minus B divided by 2A, and substituting A equals negative 5, and b equals 40 gives x equals minus 40 divided by 2 multiplied by negative 5, which simplifies to 40 divided by 10, giving 4. Thus, the maximum profit occurs when 4 units are sold. Substituting x equals 4 into the profit function gives p multiplied by 4 equals negative 5 multiplied by 4 squared plus 40 multiplied by 4 minus 100, which equals negative 80, plus 160 minus 100, giving negative 20. This means the maximum profit is negative £20, indicating a loss even at the optimal output level. We then consider exponential growth using compound interest. Given an initial investment of 500,000 shillings, an annual compound interest rate of 8%, and time measured in years, the value after t years is given by p multiplied by t equals 500,000 multiplied by 1 plus 0.08 raised to the power of t. After 5 years, p multiplied by 5 equals 500,000 multiplied by 1.08 raised to the power of 5, which is approximately 734,650 shillings. To find how long it takes for the investment to double, we set 500,000 multiplied by 1.08 raised to the power of t equal to 1 million, divide both sides by 500,000 to get 1.08 raised to the power of t equals 2, and then take natural logarithms. This gives t multiplied by ln 1.08 equals ln 2, so t equals ln 2 divided by ln 1.08, which is approximately 9 years. Next, we examine exponential decay. A machine's value is given by V multiplied by T equals 1,200,000 multiplied by 0.85 raised to the power of T. After 4 years, V multiplied by 4 equals 1,200,000 multiplied by 0.85 raised to the power of 4, which is approximately 626,400 shillings. To find when the value falls below 500,000 shillings, we set up an inequality and solve using logarithms. Because the natural logarithm of 0.85 is negative, dividing by it reverses the inequality, giving t greater than approximately 5.37. This means the value falls below 500,000 shillings after about 5.37 years. We then consider an investment doubling period with a principal of 1 million shillings and an annual interest rate of 6%. The value after t years is P multiplied by T equals 1 million multiplied by 1.06 raised to the power of T. Setting this equal to 2 million and solving using natural logarithms gives T equals ln 2 divided by ln 1.06, which is approximately 11.9 years. Finally, we examine depreciation with an initial value of 2 million shillings and a depreciation rate of 20% per year, giving V multiplied by T equals 2 million multiplied by 0.8 raised to the power of T. Solving the inequality to find when the value falls below 800,000 shillings gives T greater than approximately 4.11 years. As we bring this session to a close, please take a moment to reflect on how mathematical functions support real business decisions, from pricing and production to investment and asset management. Do continue to use the chat section to ask questions or seek clarification. I now encourage you to pause, take a 5-minute break and then return refreshed and ready to continue, in line with the flexible Synapse learning model. We now move into the next major area of our course, which is matrix algebra. As always, I encourage you to remain active during the session and to use the chat section whenever you need clarification, because matrices are a powerful tool in business analysis and must be understood carefully from the foundations. By the end of this section, you should be able to understand the definition and basic properties of matrices, perform key matrix operations such as addition, subtraction, multiplication, transposition, and inversion, and apply matrices to solve business problems including statistical modeling, input-output analysis, and Markov analysis. A matrix is defined as a rectangular array of numbers arranged in rows and columns. Matrices are fundamental in many areas of quantitative analysis because they allow us to represent and manipulate large amounts of data efficiently, particularly when dealing with systems of equations, linear relationships, and complex business interactions. A matrix is usually denoted by a capital letter such as A, B, or C. The individual numbers within a matrix are called elements, and each element is identified by 2 subscripts that show its position. For example, A with subscript ij represents the element located in the ith row and the jth column of matrix A. In general terms, a matrix consists of m rows and n columns, and this size is referred to as the order of the matrix. Understanding the structure of a matrix is essential before performing any operations on it. So if this notation feels unfamiliar, please raise it in the chat, and we will revisit it. There are several important types of matrices that you need to recognize. A row matrix is a matrix that has only one row, such as a 1 by 3 matrix containing the elements 3, 4, and 5. A column matrix has only one column, such as a 3 by 1 matrix containing the elements 3, 2, and 6. A square matrix has the same number of rows and columns, for example a 2 by 2 matrix with elements 1, 2, 3, and 4. A zero matrix is a matrix in which all elements are 0. An identity matrix is a special square matrix in which all diagonal elements are 1 and all other elements are 0, and it plays a role similar to the number 1 in ordinary arithmetic. A diagonal matrix is a square matrix where all non-diagonal elements are 0. A symmetric matrix is a square matrix that is equal to its transpose, meaning it looks the same when rows and columns are interchanged. A skew-symmetric matrix is also square, but in this case the transpose of the matrix is the negative of the original matrix. We now consider matrix operations, beginning with matrix addition and subtraction. Two matrices can only be added or subtracted if they have the same dimensions, meaning the same number of rows and columns. The operation is carried out by adding or subtracting corresponding elements. For example, if matrix A contains the elements 1, 2, 3, and 4 arranged in 2 rows and 2 columns, and matrix B contains 5, 6, 7, and 8 arranged in the same way, then A plus B is obtained by adding 1 and 5, 2 and 6, 3 and 7, and 4 and 8, giving a new matrix with elements 6, 8, 10, and 12. Matrix multiplication follows different rules. To multiply two matrices, the number of columns in the first matrix must be equal to the number of rows in the second matrix. The multiplication is carried out by multiplying the rows of the first matrix by the columns of the second matrix, and then adding the results. For example, when multiplying a 2 by 3 matrix by a 3 by 2 matrix, each element in the resulting matrix is formed by taking a row from the first matrix, a column from the second matrix, multiplying corresponding elements, and summing the products. This process produces a new matrix whose dimensions depend on the outer dimensions of the original matrices. Another important operation is matrix transposition. The transpose of a matrix is obtained by swapping its rows and columns. For instance, if matrix A has elements A, B in the first row and C, D in the second row, then the transpose of A has A and C in the first row, and B and D in the second row. Transposition is widely used in both theoretical and applied matrix work, especially in statistics and optimization. Matrix inversion is one of the most powerful, but also most restrictive operations. A square matrix A is said to be invertible if there exists another matrix, called the inverse of A, such that A multiplied by its inverse gives the identity matrix, and the inverse multiplied by A also gives the identity matrix. Not all matrices are invertible, and only square matrices can have inverses. For a 2 by 2 matrix with elements A, B, C, and D, the inverse is given by 1 divided by AD minus BC, multiplied by a matrix in which D and A swap positions, and B and C change signs. A crucial condition is that AD minus BC must not equal 0. If it equals 0, the matrix is singular and has no inverse. To illustrate this, consider a 2 by 2 matrix with elements 2, 3, 4, and 5. The determinant is calculated as 2 multiplied by 5, minus 3 multiplied by 4, which gives 10, minus 12, resulting in negative 2. Since this is not 0, the matrix is invertible. The inverse is obtained by dividing each element of the adjusted matrix by negative 2, producing a matrix with elements negative 2.5, 1.5, 2, and negative 1. For 3 by 3 matrices, the process is more involved. The determinant is calculated using the formula A multiplied by EI minus FH, minus B multiplied by DI minus FG, plus C multiplied by DH minus EG. Once the determinant is found, the adjoint of the matrix is calculated by forming the cofactor matrix and then transposing it. The inverse is then obtained by multiplying the adjoint by 1 divided by the determinant. Although the procedure is longer, the underlying logic remains the same, and it is particularly important in solving larger systems of equations. Matrix operations have wide-ranging applications in business. In economic modeling, particularly input-output analysis, matrices are used to represent the flow of goods and services between different sectors of the economy. In statistical analysis, matrices are essential in multivariate analysis and regression models, where large datasets are represented and manipulated efficiently. In optimization and linear programming, matrices are used to represent constraints and objective functions, and matrix inversion plays a key role in solving systems of linear equations. We now turn to the practice question to consolidate these ideas. You are given two 3x3 matrices A and B. In part A, matrix addition is performed by adding corresponding elements of A and B, producing a matrix in which every element is 10. In part B, matrix multiplication is carried out by multiplying the rows of matrix A by the columns of matrix B, resulting in a new matrix with elements 30, 24, and 18 in the first row, 84, 69, and 54 in the second row, and 138, 114, and 90 in the third row. In part C, the transpose of matrix A is obtained by swapping rows and columns, giving rows 147, 258, and 369, while the transpose of matrix B gives rows 963, 852, and 741. In part D, the determinant of matrix A is calculated using the 3x3 determinant formula, and the final result is 0. This confirms that matrix A is singular and does not have an inverse. As we conclude this session, please take time to reflect on how matrices allow us to handle complex business data in a structured and efficient way. Do not hesitate to use the chat section to ask questions or request further explanation, especially on matrix multiplication and inversion, as these are areas students often find challenging at first. I now encourage you to pause, take a 5-minute break, and then return refreshed and ready to continue, in line with the flexible Synapse learning model. We continue by examining the application of matrices in real business and analytical contexts. As we proceed, I encourage you to remain engaged and to use the chat section at any point if you need clarification, because this topic brings together theory and practice in a very direct way. Matrices are extensively used in analytical and computational techniques across economics, business analysis, and decision-making processes. In this section, we focus on their application in statistical modeling, Markov analysis, input-output analysis, and several general areas. In statistical modeling, matrices are used to represent and analyze relationships between multiple variables simultaneously. This approach is common in regression analysis, multivariate analysis, and time series forecasting. By organizing data into matrices, we can efficiently represent large datasets, compute relationships between variables, and solve for unknown values in complex models. A key example of statistical modeling using matrices is multiple linear regression. Multiple linear regression is used to predict a dependent variable using several independent variables. The system of equations representing multiple regression can be written in matrix form as y equals x multiplied by beta plus epsilon. In this expression, y is a vector of observed dependent variables such as sales revenue, x is a matrix of independent variables such as advertising expenditure and price, beta is a vector of unknown regression coefficients, and epsilon is a vector of errors. The solution for the regression coefficients is given by beta hat equals the inverse of x transpose multiplied by x transpose multiplied by y. This formula involves matrix multiplication and matrix inversion and allows us to estimate the coefficients of the regression model. In practice, statistical software applies this formula to fit regression models to real data. From a business perspective, a company might use this type of matrix-based regression to predict future sales based on factors such as advertising spend, pricing strategies, and product quality, and then use the estimated coefficients to identify which factors have the greatest influence on sales. If this regression structure feels abstract, please ask in the chat, and we will unpack it step by step. We now turn to Markov analysis. Markov analysis is a probabilistic modeling technique used to analyze systems that move between different states over time. A key feature of a Markov process is that the future state depends only on the current state and not on the sequence of past states. Matrices are used to represent the probabilities of moving from one state to another through what is known as a transition matrix. For example, consider a system with two states, state A and state B. The transition matrix P consists of probabilities showing movement between these states. The first row shows the probability of remaining in state A and the probability of moving from state A to state B, while the second row shows the probability of moving from state B to state A and remaining in state B. In a business context, Markov analysis is widely used in marketing. Firms can model customer behavior by estimating the probability that a customer will remain loyal, switch brands, or make repeat purchases. Transition matrices help businesses understand patterns of customer retention and switching, supporting better strategic decisions. Another important application of matrices is input-output analysis. Input-output analysis is an economic technique used to study the interrelationships between different sectors of an economy. It shows how the output of one industry becomes the input of another industry. The main tool used in this analysis is the input-output matrix. For example, consider an economy with two sectors, agriculture and manufacturing. The input-output matrix A contains elements that show how much output from agriculture is used in agriculture, how much from agriculture is used in manufacturing, how much from manufacturing is used in agriculture, and how much from manufacturing is used in manufacturing. To determine the total output required to meet a given level of final demand, we use the Leontief model, which is written as x equals the inverse of I minus A multiplied by y. Here, x represents total output, I is the identity matrix, A is the input-output matrix, and y is the vector of final demand. This model is extremely useful for governments and policymakers, as it allows them to assess how changes in demand or investment in one sector affect the rest of the economy. For instance, increased government spending in manufacturing may create ripple effects across agriculture and services. Beyond these core areas, matrices have a wide range of general applications. In data analysis, matrices are central to principal component analysis, which reduces the dimensionality of large datasets while retaining the most important information. This is especially useful when dealing with many correlated variables. In image processing, images are represented as matrices, in which each element corresponds to the intensity of a pixel, and matrix operations are used for filtering, edge detection, and transformations. In computer graphics, matrices are used to perform transformations such as translation, rotation, and scaling of objects, allowing points, such as x and y coordinates, to be manipulated efficiently. In network analysis, matrices are used to represent connections between nodes, such as cities in a transport network, where matrix entries indicate whether a direct route exists between pairs of cities. As we conclude this session, take a moment to reflect on how matrix methods extend far beyond abstract mathematics and play a crucial role in real business, economic, and technological applications. Please use the chat section to ask questions or seek clarification, especially on regression models, Markov transitions, or input-output analysis, as these are areas you will encounter again later in the course. I now encourage you to pause, take a 5-minute break, and then return refreshed and ready to continue, in line with the flexible Synapse learning model. We now move into an important pillar of quantitative analysis, which is calculus. Please remain attentive as we proceed, and feel free to use the chat section at any point to ask questions or seek clarification, because calculus underpins many key decisions in business and finance. By the end of this section, you should be able to understand the basic concepts of differentiation and integration in business contexts, apply the rules of differentiation and integration to real-world business problems, and interpret the economic meaning of derivatives and integrals. Calculus is the branch of mathematics that focuses on rates of change and accumulation. It consists of two main areas. Differentiation is concerned with measuring how one quantity changes in response to another, while integration focuses on measuring the total or accumulated effect of change. In business, calculus is widely used in marginal analysis, optimization of cost and revenue, and forecasting future trends. We begin with differentiation. Differentiation refers to finding the derivative of a function, which tells us how the value of a function changes as its input changes. In business terms, derivatives often represent marginal values, such as marginal cost, marginal revenue, or the rate of change of profit or sales. The derivative of a function gives the slope of the function at a particular point, which represents the rate of change of the dependent variable with respect to the independent variable. Several basic rules of differentiation are essential. The power rule states that the derivative of x raised to the power n is n multiplied by x raised to the power n minus 1. The sum and difference rule states that the derivative of the sum of two functions is the sum of their derivatives, and the derivative of the difference of two functions is the difference of their derivatives. The constant multiple rule states that if a function is multiplied by a constant, the derivative is the constant multiplied by the derivative of the function. The product rule states that the derivative of the product of two functions is the derivative of the first function multiplied by the second function plus the first function multiplied by the derivative of the second function. The quotient rule states that the derivative of one function divided by another is the derivative of the numerator multiplied by the denominator minus the numerator multiplied by the derivative of the denominator, all divided by the square of the denominator. The chain rule states that when a function is composed of another function, the derivative is obtained by differentiating the outer function evaluated at the inner function and multiplying by the derivative of the inner function. To see differentiation in a business context, consider a cost function given by c multiplied by x equals 5x squared plus 10x plus 20, where c multiplied by x represents the total cost of producing x units. To find the marginal cost, which is the rate of change of total cost with respect to output, we differentiate the cost function. The derivative is 10x plus 10. This marginal cost function tells us how much total cost increases when production increases by one additional unit. We now turn to integration. Integration is the inverse of differentiation and is used to find the total accumulated quantity when the rate of change is known. In business, integration is often used to find total cost from marginal cost, total revenue from marginal revenue, or measures such as consumer surplus. The indefinite integral of a function represents accumulation and is written as the integral of the function with respect to x. The basic rules of integration mirror those of differentiation. The power rule for integration states that the integral of x raised to the power n is x raised to the power n plus 1 divided by n plus 1, plus a constant of integration, provided n is not negative 1. The sum and difference rule states that the integral of a sum or difference of functions is the sum or difference of their integrals. The constant multiple rule states that the integral of a constant multiplied by a function is the constant multiplied by the integral of the function. As an example, suppose the marginal revenue function of a company is 10x plus 20. To find the total revenue function, we integrate this expression. The result is 5x squared plus 20x plus a constant. If the company has fixed revenue of £1,000 when no units are sold, Substituting x equals 0 gives the constant as 1000. The total revenue function, therefore, becomes 5x squared plus 20x plus 1000. This function gives the total revenue earned from selling x units. Calculus has several important applications in business. Marginal analysis uses differentiation to evaluate marginal cost, marginal revenue, and marginal profit, helping firms decide optimal levels of production and pricing. Optimization involves finding maximum or minimum values of functions, such as maximum profit or minimum cost, by setting the derivative equal to 0 and solving for critical points. Integration is used to calculate consumer and producer surplus by measuring areas under curves. Total cost, total revenue, and total profit are obtained by integrating marginal functions, while their rates of change are analyzed using differentiation. We now consider the practice questions. In the first question, the profit function in thousands of shillings is given by p multiplied by x equals negative 5x squared plus 60x minus 100, where x represents the number of units produced in hundreds. To find the level of production that maximizes profit, we differentiate the profit function to obtain negative 10x plus 60. Setting this equal to 0 gives 10x equals 60, so x equals 6. The second derivative is negative 10, which confirms that this point is a maximum. Substituting x equals 6 into the profit function gives negative 5 multiplied by 36 plus 360 minus 100, which equals 80. This means the maximum profit is 80,000 shillings. When no units are produced, substituting x equals 0 gives negative 100, meaning a loss of 100,000 shillings. In the second question, the marginal cost function is 4x minus 20 and the fixed cost is 500 shillings. Since marginal cost is the derivative of total cost, we integrate 4x minus 20 to obtain 2x squared minus 20x plus a constant. Using the fixed cost condition that total cost at 0 units is 500 gives the constant as 500. The total cost function is therefore 2x squared minus 20x plus 500. Substituting x equals 10 gives a total cost of 500,000 shillings. This result shows that at this level of output, the fixed cost dominates because the variable cost terms cancel out. We then consider a revenue function given by 1000 multiplied by e raised to the power 0.05 t, where t represents time in months. To find the rate of change of revenue, we differentiate with respect to time, giving 50 multiplied by e raised to the power 0.05 t. Substituting t equals 12 gives 50 multiplied by e raised to the power 0.6, which is approximately 91.1. This means that after 12 months, revenue is increasing at a rate of approximately 91,100 shillings per month, reflecting continuous exponential growth. This same interpretation applies to the final question, which again asks for the rate of change of revenue at 12 months using the same revenue function. The calculated rate confirms that revenue growth after 1 year is approximately 91,100 shillings per month. As we conclude this calculus section, take time to reflect on how differentiation and integration provide powerful tools for analyzing cost, revenue, profit, and growth in business contexts. Please continue to use the chat section to ask questions or request clarification, especially on optimization and interpretation of marginal values. I now encourage you to pause, take a 5-minute break, and then return refreshed and ready to continue, in line with the flexible Synapse learning model. We continue our work on differentiation, focusing carefully on its meaning, purpose, and direct application to business problems. As always, please feel free to use the chat section at any time to ask questions or seek clarification, because a strong grasp of differentiation is essential for marginal analysis and decision-making in business. By the end of this section, you should be able to understand what differentiation means and why it is important in business applications. Apply differentiation to find rates of change of cost, revenue, and profit functions. Use marginal analysis to solve business problems and interpret the economic meaning of derivatives. Differentiation is the process of calculating the derivative of a function. The derivative of a function represents the rate of change of the output with respect to the input. In practical terms, it tells us how much one variable changes when another variable changes by a very small amount. This idea is particularly useful in business, where managers are often interested in marginal effects, such as how total cost changes when one more unit is produced, or how revenue changes when one more unit is sold. Mathematically, the derivative of a function can be written as f prime multiplied by x, or as d by dx applied to the function. The derivative measures how much the value of the function changes as the value of x changes slightly. In business contexts, this allows us to analyze marginal cost, marginal revenue, and marginal profit. For example, rather than looking at total cost, a firm is often more interested in how cost changes when output increases by 1 unit, and that is exactly what the derivative provides. For a function that is continuous and differentiable, the derivative at a particular point gives the slope of the tangent line to the graph at that point. This slope represents the instantaneous rate of change. If the derivative is positive at a point, the function is increasing there. If the derivative is negative at a point, the function is decreasing. If the derivative is 0, the function has a stationary point, which may be a maximum, a minimum, or a point of inflection. These interpretations are extremely important in optimization problems in business. To understand differentiation intuitively, consider a company whose total revenue is given by a function R multiplied by x, where x represents the number of units sold. If we want to know how revenue changes as sales increase, we calculate the derivative of the revenue function. The resulting expression, R prime multiplied by x, is the marginal revenue. This tells the firm how much extra revenue it earns from selling one additional unit of output. Differentiation has several important business applications. Marginal cost is defined as the derivative of the total cost function C multiplied by x with respect to x. It represents the additional cost incurred by producing one more unit. For example, if the total cost function is C multiplied by x equals 5x squared plus 10x plus 20, then the marginal cost is obtained by differentiating this expression, giving 10x plus 10. This marginal cost function tells us how total cost changes when production increases slightly. Marginal revenue is the derivative of the total revenue function with respect to the number of units sold. It shows the additional revenue generated from selling one more unit. For example, if the total revenue function is R multiplied by x equals 10x squared plus 50x plus 100, then differentiating gives marginal revenue equal to 20x plus 50. This tells us the rate at which revenue is changing as sales increase. Differentiation is also central to profit maximization. Profit is defined as revenue minus cost, and by differentiating the profit function and setting the derivative equal to 0, firms can find critical points where profit may be maximized or minimized. The second derivative test is then used to determine whether a critical point corresponds to a maximum or a minimum. Differentiation is also used in elasticity of demand analysis, where the sensitivity of quantity demanded to changes in price is measured using derivatives of the demand function. To apply differentiation effectively, we need to understand the derivatives of common functions. The power rule states that if a function is x raised to the power n, then its derivative is n multiplied by x raised to the power n minus 1. The derivative of a constant is 0. The sum and difference rule states that the derivative of a sum or difference of functions is the sum or difference of their derivatives. The product rule states that the derivative of the product of two functions is the derivative of the first multiplied by the second, plus the first multiplied by the derivative of the second. The quotient rule states that the derivative of one function divided by another is the derivative of the numerator multiplied by the denominator minus the numerator multiplied by the derivative of the denominator, all divided by the denominator squared. The chain rule states that for a composite function, the derivative is the derivative of the outer function evaluated at the inner function multiplied by the derivative of the inner function. To illustrate differentiation in a business setting, consider a revenue function given by r multiplied by x equals 15x squared plus 50x. Differentiating this function gives marginal revenue equal to 30x plus 50. This means that for each additional unit sold, revenue increases according to this expression. If the company has sold 10 units, substituting x equals 10 gives marginal revenue equal to 30 multiplied by 10 plus 50, which equals 300 plus 50, giving 350. This means that selling the 11th unit increases revenue by £350. We now turn to the practice questions. In the first question, the total cost function, measured in thousands of shillings, is C multiplied by x equals 0.5x cubed minus 4x squared plus 10x plus 50, where x is the number of units produced. The marginal cost function is found by differentiating the total cost function, giving 1.5x squared minus 8x plus 10. To find the marginal cost, when x equals 5, we substitute 5 into this expression, giving 1.5 multiplied by 25 minus 40 plus 10, which equals 37.5. Minus 40 plus 10, resulting in 7.5. This means the marginal cost, at 5 units, is 7.5 thousand shillings. Interpreting this result, producing the 6th unit increases total cost by approximately 7,500 shillings. In the second question, the profit function, measured in thousands of shillings, is P multiplied by x equals negative 2x cubed plus 15x squared plus 36x minus 40, where x is the number of units produced in hundreds. Differentiating the profit function gives negative 6x squared plus 30x plus 36. Setting this equal to 0 and simplifying gives x squared minus 5x minus 6 equals 0. Solving this quadratic gives two critical points, x equals 6 and x equals negative 1. To determine which point gives maximum profit, we calculate the second derivative, which is negative 12x plus 30. Evaluating this at x equals negative 1 gives a positive value, indicating a minimum. Therefore, maximum profit occurs at x equals 6. Substituting x equals 6 into the profit function gives a profit of 284,000 shillings. In the final question, the revenue function is R multiplied by x equals 150x minus 0.5x squared, where x is the number of units sold. Differentiating this function gives marginal revenue equal to 150 minus x. When x equals 100, marginal revenue is 150 minus 100, which equals 50. This means that when 100 units have been sold, selling 1 additional unit increases total revenue by approximately 50 shillings. This interpretation is consistent with earlier marginal analysis, where marginal values estimate the change resulting from 1 additional unit of output or sales. As we conclude this session, please reflect on how differentiation allows businesses to understand rates of change, marginal values, and optimal decision points. Do continue to use the chat section to ask questions or request clarification, especially on interpreting marginal results and optimization problems. I now encourage you to pause, take a 5-minute break, and then return refreshed and ready to continue, in line with the flexible Synapse learning model. We continue our study of differentiation by focusing specifically on the rules of differentiation and how they are applied to more complex business functions. Please remember that you are encouraged to use the chat section at any time if you need clarification, because mastering these rules is essential for analyzing cost, revenue, and profit accurately. By the end of this section, you should be able to understand and apply the general rule of differentiation, use the chain rule, product rule, and quotient rule to differentiate more complex functions, solve business-related problems involving marginal cost, marginal revenue, and marginal profit, and interpret the results of differentiation in business contexts. Differentiation allows us to understand how a function responds to small changes in the independent variable, and these rules simplify the process of finding derivatives when functions become more complicated. We begin with the general differentiation rule, also known as the power rule. This rule applies to functions of the form x raised to the power n, where n is any real number. The derivative of such a function is n multiplied by x raised to the power n minus 1. For example, if a function is 3x raised to the power 4, the derivative is 12x cubed. This rule is widely used in business because many cost, revenue, and profit functions are expressed as polynomials. We now consider the chain rule. The chain rule is used when differentiating a composite function, meaning a function nested inside another function. In this situation, we differentiate the outer function first and then multiply by the derivative of the inner function. For example, consider a function defined as the quantity 3x plus 2 raised to the power 5. To differentiate this function, we first differentiate the outer power, giving 5 multiplied by the quantity 3x plus 2 raised to the power 4, and then multiply by the derivative of the inner expression, which is 3. The final derivative is 15 multiplied by the quantity 3x plus 2 raised to the power 4. The chain rule is particularly important in business models where functions involve transformations, such as growth rates, taxes, or cost adjustments applied to other variables. Next, we examine the product rule. The product rule is used when a function is defined as the product of two separate functions. The derivative is found by differentiating the first function and multiplying it by the second, and then adding the first function multiplied by the derivative of the second. For example, if a function is defined as the product of 2x plus 3 and x squared minus 5, we first differentiate 2x plus 3 to get 2, and differentiate x squared minus 5 to get 2x. Applying the product rule gives 2 multiplied by the quantity x squared minus 5 plus the quantity 2x plus 3 multiplied by 2x. Simplifying this expression results in 6x squared plus 6x minus 10. This rule is useful in business when revenue, cost, or profit is expressed as the interaction of two changing factors. We then move to the quotient rule. The quotient rule is applied when one function is divided by another. The derivative is found by differentiating the numerator and multiplying it by the denominator, subtracting the numerator multiplied by the derivative of the denominator, and then dividing the entire expression by the square of the denominator. For example, if a function is defined as 2x plus 3 divided by x squared minus 5, we differentiate the numerator to get 2 and the denominator to get 2x. Substituting into the quotient rule gives 2 multiplied by the quantity x squared minus 5 minus the quantity 2x plus 3 multiplied by 2x, all divided by the quantity x squared minus 5 squared. Simplifying leads to negative 2x squared minus 6x minus 10 divided by the quantity x squared minus 5 squared. This rule is commonly used in business analysis when average measures or ratios are involved. Differentiation has several important applications in business. Marginal cost is obtained by differentiating the total cost function with respect to output and tells the firm how much total cost increases when one additional unit is produced. Marginal revenue is obtained by differentiating the total revenue function and shows the additional revenue earned from selling one more unit. Profit maximisation is achieved by differentiating the profit function, setting the first derivative equal to 0 to find critical points, and then using the second derivative test to determine whether the result corresponds to a maximum or a minimum. Differentiation is also used to calculate elasticity of demand, which measures how sensitive quantity demanded is to changes in price. We now work through the practice questions. In the first question, the total cost function is given as 4x cubed plus 2x squared minus 5x plus 10. To find the marginal cost, we differentiate this function. The derivative of 4x cubed is 12x squared, the derivative of 2x squared is 4x, the derivative of minus 5x is minus 5, and the derivative of 10 is 0. The marginal cost function is therefore 12x squared plus 4x minus 5. To find the marginal cost when 3 units are produced, we substitute x equals 3 into this expression, giving 12 multiplied by 9 plus 12 minus 5, which equals 108 plus 12 minus 5, resulting in 115. This means that producing the 4th unit increases total cost by approximately £115. In the second question, the total revenue function is given as 10x squared plus 30x plus 100. To find the marginal revenue, we differentiate the revenue function. The derivative of 10x squared is 20x, the derivative of 30x is 30, and the derivative of 100 is 0. The marginal revenue function is therefore 20x plus 30. Substituting x equals 4 gives marginal revenue equal to 80 plus 30, which equals 110. This means that when 4 units have been sold, selling one additional unit increases total revenue by approximately £110. As we conclude this session, take time to reflect on how the general rule, chain rule, product rule, and quotient rule allow us to analyze increasingly realistic business models. Please continue to use the chat section to ask questions or seek clarification, especially when applying these rules to complex functions. I now encourage you to pause, take a 5-minute break, and then return refreshed and ready to continue, in line with the flexible Synapse learning model. We continue our work on differentiation by focusing specifically on exponential and logarithmic functions. Please remain engaged throughout, and remember that you are encouraged to use the chat section at any time if you would like clarification, because these functions are central to modeling growth, decay, and responsiveness in business and economics. By the end of this section, you should be able to differentiate exponential and logarithmic functions. Understand the significance of their derivatives in business applications, and apply these techniques to real-world problems involving growth, decay, and elasticity. Exponential and logarithmic functions appear frequently in business models because many economic processes grow or decline at proportional rates rather than at constant absolute amounts. We begin with exponential functions. An exponential function takes the form a multiplied by b raised to the power x, where a is a constant, b is the base of the exponential and is greater than 0, and x is the independent variable. When we differentiate an exponential function of this form, the derivative is obtained by multiplying the original exponential function by the natural logarithm of the base. In words, the derivative of a multiplied by b raised to the power x is a multiplied by b raised to the power x, multiplied by the natural logarithm of b. This tells us that the rate of change of an exponential function is proportional to its current value and depends on the base of the exponential. For example, if a function is 3 multiplied by 2 raised to the power x, the derivative is 3 multiplied by 2 raised to the power x, multiplied by the natural logarithm of 2. This means that the rate of change at any point depends on both the value of 2 raised to the power x and the constant natural logarithm of 2. If at any point you are unsure why the natural logarithm appears, please raise it in the chat, and we will clarify the reasoning step by step. There is a special and very important case when the base of the exponential function is the natural number e, which is approximately 2.71828. When a function is written as a multiplied by e raised to the power x, its derivative is simply a multiplied by e raised to the power x. In words, the derivative of a multiplied by e raised to the power x is the same as the original function. This unique property is why exponential functions with base e are used so widely in calculus, finance, and economics, particularly in continuous growth and decay models. We now turn to logarithmic functions. A logarithmic function is the inverse of an exponential function, and the most commonly used logarithmic function in calculus is the natural logarithm, written as ln x. The derivative of the natural logarithm of x with respect to x is 1 divided by x. This means that the rate of change of the natural logarithm decreases as x increases, reflecting diminishing rates of change. In business terms, this behavior is useful for modeling situations where growth slows down over time. If the logarithmic function uses a base other than e, such as base b, the derivative is 1 divided by x multiplied by the natural logarithm of b. In words, the derivative of log base b of x is 1 divided by x times the natural logarithm of b. The natural logarithm of b is a constant, so the overall structure of the derivative still shows an inverse relationship with x. Exponential and logarithmic functions have many important business applications. Exponential functions are commonly used to model growth and decay. Investment growth, for example, is often represented using exponential functions when interest is compounded continuously. Asset depreciation can also be modeled using exponential decay. As an illustration, if a company invests £1,000 at an annual interest rate of 5%, the value of the investment after t years can be written as 1,000 multiplied by e raised to the power 0.05t. The rate of change of this investment value is found by differentiating the function, giving 1,000 multiplied by e raised to the power 0.05t multiplied by 0.05. This derivative tells the company how quickly the investment value is changing at any given time. Logarithmic functions are also essential in the analysis of elasticity of demand. Price. Elasticity of demand measures how responsive quantity demanded is to changes in price, and differentiation plays a key role in its calculation. For example, if the demand function is written as 1,000 multiplied by p raised to the power -2, where p is price and q is quantity demanded, differentiating with respect to price gives -2,000 multiplied by p raised to the power -3. Elasticity is then calculated by multiplying this derivative by price divided by quantity demanded, allowing firms to assess whether demand is elastic or inelastic at different price levels. Logarithmic functions are further used to model utility in economics and business. A common utility function is the natural logarithm of x, which captures diminishing marginal utility. The derivative of this function, which is 1 divided by x, represents marginal utility. This tells us that as consumption increases, the additional satisfaction gained from consuming one more unit decreases, a principle that aligns closely with observed consumer behavior. We now work through the practice questions to consolidate these ideas. In the first question, the revenue function is given as 100 multiplied by 2 raised to the power x, where revenue represents total revenue from selling x units. To find the marginal revenue, we differentiate this function. Using the exponential differentiation rule, the derivative is 100 multiplied by 2 raised to the power x, multiplied by the natural logarithm of 2. This is the marginal revenue function. To calculate the marginal revenue when 5 units are sold, we substitute x equals 5, giving 100 multiplied by 2 raised to the power 5, multiplied by the natural logarithm of 2. 2 raised to the power 5 is 32, and the natural logarithm of 2 is approximately 0.6931, giving a marginal revenue of approximately £2,217.92. In the second question, the demand function is given as 500 multiplied by p raised to the power negative 1.5, where q is quantity demanded and p is price. To find the rate of change of demand with respect to price, we differentiate with respect to p. The derivative is negative 750 multiplied by p raised to the power negative 2.5. To find the rate of change of demand when the price is £10, we substitute p equals 10, giving negative 750 multiplied by 10 raised to the power negative 2.5. This evaluates to approximately negative 2.37. This result means that for every £1 increase in price when the price is £10, demand decreases by approximately 2.37 units. As we conclude this session, take time to reflect on how differentiation of exponential and logarithmic functions allows us to analyze growth, decay, responsiveness, and diminishing effects in business. Please continue to use the chat section to ask questions or seek clarification, particularly on interpreting derivatives in practical contexts. I now encourage you to pause, take a 5-minute break, and then return refreshed and ready to continue, in line with the flexible Synapse learning model. We now focus on turning points, specifically maxima, minima, and inflection points, and how these ideas are applied in business analysis. Please remember to use the chat section whenever something needs clarification, because identifying and interpreting turning points is central to optimization in cost, revenue, and profit decisions. By the end of this section, you should be able to identify turning points of a function, including local maxima, local minima, and inflection points, understand their significance in business applications such as profit maximization and cost minimization, and apply the first and second derivative tests to classify these points and analyze the behavior of functions. A turning point is a point on the graph of a function where the function changes direction. In practical terms, this means the function may stop increasing and start decreasing, or stop decreasing and start increasing. An inflection point is different, because at an inflection point the function does not necessarily change direction, but the curvature of the graph changes. There are 3 key types of turning points. A local maximum occurs when the value of the function at a point is higher than the values at nearby points, and the function changes from increasing to decreasing at that point. A local minimum occurs when the value of the function at a point is lower than the values at nearby points, and the function changes from decreasing to increasing. An inflection point occurs when the function changes its concavity, meaning it changes from being concave up, shaped like a U, to concave down, shaped like an upside-down U, or the other way round. At an inflection point, the second derivative changes sign, but the point is not necessarily a maximum or a minimum. To identify and classify turning points, we rely on the first and second derivatives. According to the first derivative test, if the derivative is equal to 0 at a particular value of x, and the derivative changes sign around that value, then that value corresponds to a turning point. If the derivative changes from positive to negative, the function has a local maximum there. If the derivative changes from negative to positive, the function has a local minimum. The second derivative test gives a quicker method when the first derivative is 0. If the second derivative evaluated at that point is positive, the function has a local minimum because the graph is concave up. If the second derivative evaluated at that point is negative, the function has a local maximum because the graph is concave down. If the second derivative evaluated at that point is 0, the test is inconclusive and further analysis is needed. To illustrate this process, consider the function given by negative 2x cubed plus 9x squared minus 12x plus 5. The first derivative is obtained by differentiating this expression, giving negative 6x squared plus 18x minus 12. Setting this equal to 0 gives negative 6x squared plus 18x minus 12 equals 0. Dividing through by negative 6 simplifies the equation to x squared minus 3x plus 2 equals 0. Factoring gives x minus 1 multiplied by x minus 2 equals 0. So the critical points are x equals 1 and x equals 2. To classify these points, we find the second derivative, which is negative 12x plus 18. Substituting x equals 1 gives 6, which is positive, so there is a local minimum at x equals 1. Substituting x equals 2 gives negative 6, which is negative, so there is a local maximum at x equals 2. This tells us exactly where the function reaches its lowest and highest values locally. We now turn to inflection points. An inflection point occurs where the concavity of the function changes, which happens when the second derivative changes sign. To find an inflection point, we first find the second derivative, then set it equal to 0, and finally check whether the second derivative changes sign around that value. For example, consider the function x cubed minus 6x squared plus 12x minus 8. The first derivative is 3x squared minus 12x plus 12, and the second derivative is 6x minus 12. Setting the second derivative equal to 0 gives x equals 2. Substituting values slightly less than 2, such as x equals 1, gives a negative value for the second derivative, indicating concave down behavior. Substituting values greater than 2, such as x equals 3, gives a positive value, indicating concave up behavior. Since the second derivative changes sign at x equals 2, this point is an inflection point. Turning points have important applications in business. Profit maximization occurs at a local maximum of the profit function, while cost minimization occurs at a local minimum of the cost function. Businesses use differentiation to locate these points and make optimal decisions about production levels and pricing. Turning points are also central to optimization problems more generally, where firms aim to maximize revenue or minimize costs. In demand and supply analysis, turning points help businesses understand where demand is increasing or decreasing most rapidly, which is valuable for strategic planning. We now consider the practice questions. In the first question, the total profit function is given by negative x cubed plus 6x squared plus 9x minus 5. To find the critical points, we first differentiate to obtain negative 3x squared plus 12x plus 9. Setting this equal to 0 gives negative 3x squared plus 12x plus 9 equals 0. Dividing by negative 3 simplifies this to x squared minus 4x minus 3 equals 0. Factoring gives x minus 3 multiplied by x plus 1 equals 0. So the critical points are x equals 3 and x equals negative 1. To classify these points, we find the second derivative, which is negative 6x plus 12. Substituting x equals 3 gives negative 6, which is negative, so there is a local maximum at x equals 3. Substituting x equals negative 1 gives 18, which is positive, so there is a local minimum at x equals negative 1. This means the profit function reaches a local maximum at x equals 3 and a local minimum at x equals negative 1. In the second question, the demand function is given by 2x cubed minus 15x squared plus 24x plus 10. Differentiating gives 6x squared minus 30x plus 24. Setting this equal to 0 gives 6x squared minus 30x plus 24 equals 0. Dividing by 6 simplifies this to x squared minus 5x plus 4 equals 0. Factoring gives x minus 4 multiplied by x minus 1 equals 0. So the critical points are x equals 4 and x equals 1. The second derivative is 12x minus 30. Substituting x equals 4 gives 18, which is positive, so there is a local minimum at x equals 4. Substituting x equals 1 gives negative 18, which is negative, so there is a local maximum at x equals 1. This tells us that demand reaches a local maximum at x equals 1 and a local minimum at x equals 4. As we conclude this session, take time to reflect on how turning points help businesses identify optimal and critical decision levels in production, pricing, and demand analysis. Please continue to use the chat section to ask questions or seek clarification, especially on applying the first and second derivative tests correctly. I now encourage you to pause, take a 5-minute break, and then return refreshed and ready to continue, in line with the flexible Synapse learning model. We now focus on the practical application of differentiation to real business problems. As we work through this material, please feel free to use the chat section whenever you need clarification. Because this topic brings together everything we have learned about derivatives and applies it directly to decision-making in business. By the end of this section, you should be able to apply differentiation to solve business problems such as maximizing profit, minimizing cost, and determining marginal revenue and marginal cost. Use differentiation in market analysis, pricing strategies, and forecasting, and understand the importance of the first and second derivative tests in optimization problems. Differentiation is a powerful analytical tool because it allows businesses to understand how key variables change and to identify optimal strategies. In practice, firms use differentiation to maximize profit, minimize cost, determine marginal values, and analyze elasticity and demand behavior. One of the most important applications of differentiation in business is profit maximization. Profit is defined as total revenue minus total cost. In words, profit as a function of output equals revenue as a function of output minus cost as a function of output. To maximize profit, we begin by finding the first derivative of the profit function, which represents marginal profit, and shows how profit changes when output increases by 1 unit. This first derivative is obtained by subtracting marginal cost from marginal revenue. To find potential maximum or minimum profit levels, we set the first derivative equal to 0 and solve for the level of output. These solutions are known as critical points. We then use the second derivative test to determine the nature of each critical point. If the second derivative is negative at a critical point, the profit function has a local maximum at that point. If the second derivative is positive, the profit function has a local minimum. To illustrate this process, consider a situation where total revenue is given by 50x minus 0.5x squared, and total cost is given by 10x plus 200. The profit function is obtained by subtracting the cost expression from the revenue expression, giving negative 0.5x squared plus 40x minus 200. Differentiating this profit function gives minus x plus 40. Setting this equal to 0 gives x equals 40. The second derivative of the profit function is negative 1, which is less than 0, confirming that this point corresponds to a local maximum. This means the company maximizes its profit by producing 40 units. Another important application of differentiation is cost minimization. Businesses aim to produce at the lowest possible cost, while maintaining quality and output requirements. The cost function represents total cost as a function of output. The first derivative of the cost function gives marginal cost, which shows how total cost changes when production increases by 1 unit. To find the output level that minimizes cost, we set the first derivative equal to 0 and solve for the critical points. We then apply the second derivative test. If the second derivative evaluated at a critical point is positive, the cost function has a local minimum at that point. For example, suppose the cost function is 2x cubed minus 30x squared plus 120x plus 100. Differentiating this function gives 6x squared minus 60x plus 120. Setting this equal to 0 and simplifying leads to two critical points, approximately 7.24 and 2.76. The second derivative of the cost function is 12x minus 60. Evaluating this at x equals 7.24 gives a positive value, indicating a local minimum. This tells us that the company minimizes its cost by producing approximately 7 units. Marginal revenue and marginal cost are central to many business decisions. Marginal revenue is the derivative of the total revenue function and measures the additional revenue earned from selling one more unit. Marginal cost is the derivative of the total cost function and measures the additional cost of producing one more unit. A key principle in economics and business is that profit is maximized when marginal revenue equals marginal cost. By setting the marginal revenue expression equal to the marginal cost expression and solving for output, firms can determine the optimal level of production. As an example, consider a revenue function given by 30x minus 0.5x squared and a cost function given by 10x plus 100. Differentiating the revenue function gives marginal revenue equal to 30 minus x, and differentiating the cost function gives marginal cost equal to 10. Setting marginal revenue equal to marginal cost gives 30 minus x equals 10, which leads to x equals 20. This means the company should produce 20 units. To maximize profit, because at this level the additional revenue from the last unit produced is exactly equal to the additional cost. Differentiation is also used in analyzing elasticity of demand. Elasticity measures how sensitive quantity demanded is to changes in price. In words, elasticity equals the derivative of quantity with respect to price multiplied by price divided by quantity. This measure helps businesses understand whether demand is elastic or inelastic and guides pricing decisions. We now turn to the practice questions. In the first question, the revenue function is given by 50x minus 0.5x squared. To find the marginal revenue function, we differentiate this expression, giving 50 minus x. To calculate marginal revenue when 20 units are sold, we substitute x equals 20 into the marginal revenue function, giving 50 minus 20, which equals 30. This means that when 20 units have been sold, selling one additional unit increases total revenue by £30. In the second question, the cost function is given by 2x cubed plus 3x squared plus 4x plus 100. Differentiating this function gives marginal cost equal to 6x squared plus 6x plus 4. To calculate the marginal cost when 5 units are produced, we substitute x equals 5 into this expression, giving 6 multiplied by 25 plus 30 plus 4, which equals 184. This means that producing the 6th unit increases total cost by £184.